All right, hello. My name is Joshua Hoblitt. I'm a principal DevOps engineer at Rubin Observatory. This talk is about my journey to embracing Rook Ceph and consolidating most of our storage needs into a single solution. It's a story of success and one that I'm hoping might convince you to try Rook as well. What I'm going to talk about, brief overview of Rubin Observatory. I cannot do it justice. I would need an entire hour to even just scratch the surface about how cool this facility is and how novel it is. But I'm just going to briefly give you a brief interview just for context. I'm going to tell you about my history with the project, what our nightly data flow looks like, why we chose Rook Ceph, what our current fleet looks like, and a few words about gitops and how that's enabled by our use of Rook. The NSF DOE ViraC Rubin Observatory is a joint initiative of the U.S. National Science Foundation and the U.S. Department of Energy's Office of Science. One of my favorite metrics to get a sense of the scale of the project is how many people there are in our community Slack workspace. There's over 5,000 members. In fact, by today, there probably are 5,000 members. Rubin Observatory is located in Chile on a mountain called Sierra Pachon. The observatory sits 2,647 meters, or 8,684 feet above sea level. Rubin Observatory was designed to address 4 key science areas: understanding the nature of dark matter and dark energy, creating an inventory of the solar system, mapping the Milky Way, and exploring the changing sky. There are currently 8 active science collaborations, which collectively have thousands of members. The field of view is approximately 10 square degrees. This is equivalent to roughly the area of 45 times a full moon. A full night of observing will produce approximately 20 terabytes of raw data and millions of alerts for transient events. In addition to the nightly rapid analysis producing transient alerts, there will be annual data releases. At the summit, we actually have 2 telescopes, the Simone Survey Telescope and the Rubin Auxiliary Telescope, which is used for data calibration. In the background of the image here, you can see Gemini South and SOAR. The base facility is located in La Serena near the coast. In addition to office spaces and logistics there, we have a 400 kVA capacity data center. The 3.2 gigapixel car-sized LSSD camera is the largest camera ever built. The camera's full focal plane is made from 189 individual 4,000 by 4,000 pixel CCDs assembled into 9 sensor arrays, referred to as RAFs. The images produced are so large that it would take 400 ultra-high definition TVs to display a single image at full resolution. The camera's range of wavelengths are divided into 6 bands associated with filters from ultraviolet to near infrared. And if you are into astronomy, those are UG, R, I, Z, and Y. These glass filters are the largest in astronomy. They're about 75 centimeters or 30 inches in diameter. Rubin's first look includes an image called the Cosmic Treasure Chest. It's focused on the southern region of the Virgo cluster. The image is about 25 square degrees, contains approximately 10 billion galaxies. The image is composed of 1,185 exposures and 4 filters, and it took approximately 10.5 hours of observing time to accumulate that. I put the link on here. I really highly encourage you to go to this link and look at it. It's an interactive thing. You can zoom in and zoom out. It's really amazing. Here's a zoomed in section of that. It shows in the foreground NGC 4411B and A. And above that, you can see a pair called RSCG55. It's a group of interacting galaxies with tidal tails between them. So the topology of the project is pretty complicated. As I mentioned, the observatory is located in Chile along with their base site, and that's where we acquire the data. The data flows from the summit to what we call the US Data Facility, which is at SLAC in California. There we do the nightly alert production, but we also have our primary archive of data, and we do some of what we call the data release production. But we also have international partners to help with that. So in the UK and in France, they actually do a portion of the data release production. So data flows from the USDF to the partners. They reduce, process all that data, they send it back to the archive center, and then complete data releases are assembled and distributed out to the various different archive sites. We also have a headquarters in Tucson, Arizona, which is where I'm located, and we do have a camera test stand there referred to as the Tucson test stand. We have built a fairly high-performance network for shipping our data from Chile to the USDF. We have multiple 100 gig redundant paths. We actually have lambdas on some subterranean cables in order to ensure that we have the bandwidth that we need. So a little bit about my history with the project. It's been a while. These things, these large experiments, they're really generational efforts. So I first heard about this project in 2002 at a conference, and back then it was proposed as the DMT, or the Dark Matter Telescope. Shortly thereafter, I started working on a different Alki survey project called PanSTARRS, and had some interaction with the Rubin team. So I was aware of the project, and we had interactions. In 2009, I joined the data management mailing list. In 2013, I assembled the long-haul network review panel. And in 2014, I started working for the project full-time at the start of what the National Science Foundation calls MREFC, or Major Research Equipment Facilities Construction. In 2019, I pivoted to working on infrastructure at the summit and the base. And in early 2020, I made my first deployment of Rook Ceph. This is a little bit of an internal joke, but the first data management project manager, Jeff Cantor, liked to say, the spice must flow whenever we were talking about data. And this really sticks with me, and this is my attempt to get AI to visualize what has been in my head for years. So our data path. I wanted to give a quick overview of what our nightly flow of data looks like. Our data starts out in the sky, and then is captured by LSST cam. Data is read from the camera electronics by the Data Acquisition System, or DAC. The DAC is located in the main Summit data center and is connected to the camera via fiber optics that run through cable wraps. The DAC is sized with enough internal storage to hold at least 3 nights of raw data. Data is read from the DAC by the camera control system diagnostic cluster nodes. Say that 3 times fast. All 10 nodes of this cluster are directly connected to the DAC. Data is read out in parallel over just common 10 gigabit per second Ethernet. This is the step at which the raw binary format of the camera electronics is transformed into the common, at least common in astronomy, FITS image format, and it's compressed. The size of a full focal plane exposure varies, depends on where we're looking in the sky, how bright the sky is, are we in the galactic plane, et cetera. But it varies between 2 and 3 gigabytes. The DC nodes then send data in parallel, again, over 10 gigabit Ethernet interfaces to the embargo rack at the US data facility. A second copy is pushed to a local RGW instance. In both cases, RGW's bucket notification support is used to send notifications to a Kafka channel, which triggers ingestion into a component we call the Observatory Operations Data Service, or OODS. On the USDF side, RGW's HTTP notification support is also used to trigger the rapid analysis. The RGW instance of the Summit is sized to hold 30 nights worth of observations. It's approximately 3 petabytes that's in use for that currently. Within the USDF, data lives in the embargo cluster long enough for rapid analysis, and then after an 80-hour embargo period is over, it's copied into another data storage system. So, why did we decide to adopt Ceph? I'm going to try to answer that question in a couple of slides and skip over it for the moment. So, once we decided to use Ceph, why did we decide to use Rook Ceph? Why not deploy Ceph with Ceph Atom, Ansible, Puppet? Well, the short answer is that Rook made it so easy to get started with Ceph that I never got around to it. Before our first Rook Ceph deployment went into production, Rook is at least as good as I am lazy. Rook fit so well into our operational model that it was obviously the correct choice for us. Before considering Rook, a good question to ask might be, why Kubernetes? Kubernetes is an orchestration engine for complex distributed applications, just like Ceph. If your team has expertise with Kubernetes, it can simplify operations, deploy as many applications on it as possible, Ceph included, and that was the case for our team. I spent a lot of time yesterday speaking to people about why they weren't using Rook. I think most of the answers kind of boiled down to a lack of experience with Kubernetes, or perhaps a fear of Kubernetes. So if a Rook Ceph workshop or some other resource that you might need to get started with Rook Ceph is something that you would find helpful, please come find me afterwards and talk to me. I'm interested in possibly trying to organize something to help people get started. Okay, so for context, why we made the decisions that we made, our team is 10 people, and that's responsible for the Summit base and the Tucson test stand. There's no dedicated storage administrators. it's definitely unlikely that there will be dedicated storage administrators in the future. So Rook helped us leverage our existing Kubernetes knowledge to deploy Ceph without building a dedicated storage silo. There are about a total of 7 people in the team who touch Rook Ceph, all of whom have provisioned Rook Ceph cluster on bare metal. I probably spend more time working on storage than anyone else in the team. I guess that I spend a little bit less than half of my time working on storage, and that time is probably divided equally between working on testing, benchmarking, provisioning new storage, doing updates, and contributing upstream to Rook. So now I'm going to try and answer the question of why Ceph. Prior to 2020, we had been deploying our services onto Kubernetes on public cloud, and to a limited extent onto an on-prem private cloud. This was such a success, the decision was made to start deploying critical components of the observatory control system to on-premises Kubernetes clusters. I had lobbied hard in favor of this change, but now I was like the dog that caught the car. I needed to solve the problem. And the problem is that mainline Kubernetes doesn't include a persistent storage facility, nor do most Kubernetes distributions have a turnkey solution. Kubernetes on public cloud uses that service as block storage, and I needed to find a solution to provide local block storage for our on-premises clusters. Rook is the default solution to that problem, and for good reason. It's a CNCF graduated project, and in my team, CNCF projects go immediately to the top of the evaluation list. It's a very strong brand for us. We've had great success with using CNCF projects. It's a sign of maturity and project management. Rook has great quick start docs. Devs are active on Slack to answer questions. Thank you, Travis. Has reasonable defaults, good enough to get a working Ceph installation without having to deeply understand Ceph's architecture, and it's packaged up as Helm charts, which is familiar and easily approachable for Kubernetes operators. Basically, Rook makes it simple to get persistent PVCs working and hides a lot of the initial complexity in deploying a Ceph cluster. This ability to be incrementally exposed to and have to reason about the complexities of Ceph was critical to allow us as a small team to be able to adopt Ceph. It just got us over that initial hump to get going with it. So the initial use of Rook Ceph was successful, then we had a new problem. Users of Jupyter notebooks wanted to have persistent home directories, scratch space for processing data. And up to this point, the baseline plan had been to use NAS appliances for shared data, which were popular in the HPC community at the time. The initial unit had been shipped to Chile, but we needed to support Jupyter notebooks at the Tucson test stand, and didn't have time to wait for our procurement cycle to run its course and get a NAS appliance in Tucson, nor have we budgeted for it. Since Rook Ceph was already deployed, it was an easy decision to try NFS exports to CephFS. Actually, we could be mounting CephFS directly into the notebook pods, and this is something we might try to transition in the future, but there was already a stopgap solution being used of NFS exports from bare metal servers, and the path of least resistance was to keep storage access as NFS while the back end was migrated around. Also, using NFS means we don't have to expose the OCs externally to the Kubernetes cluster. This is the point at which we started to question the baseline plan of using NAS appliances. NFS performance with Ganesha didn't like it was going to be a great fit for data processing, but completely acceptable for notebooks. However, around this time, there started to be interest in moving data processing from shared file systems to object storage in order to make it easier to run our science pipelines outside of a traditional HPC environment, for example, doing testing on public cloud. This opened the door for seriously considering consolidating block for Kubernetes and shared file system to being just Rook Ceph and eliminating the NAS appliances. Great. So now I need S3. At this point, it would have been crazy for us to select anything but RGW. So of course, I wasted a lot of time evaluating a different object store before seeing the light. The answer was obvious. RGW has the performance, it has the features we need, it has bucket notifications, and we already had Rook Ceph in production. So, can there be only one? Could we consolidate everything into Rook Ceph? Ceph has some very appealing properties. No out-of-tree kernel modules to have to deal with updates without scheduling major downtime. Rook makes this so painless you have to believe it to try it. I mean, we keep looking around and thinking, where's the pain going to be? And it just hasn't come. The answer we came to is yes, but with a qualification. Ceph is our default consolidated storage solution. However, we have a couple of applications deployed on Kubernetes that are sensitive to IOPS, or really sensitive to latency. And I think that is, it's because they constantly call fsync. So these few special cases, we pass through local storage from the Kubernetes nodes. This is definitely suboptimal. It turns these nodes from cattle into special snowflakes. In fairness, low latency, high ops over network attack storage is a non-trivial problem. In the end, there could be almost only one. Also say, generally, it checks a lot of boxes for us, especially enabling gitops. There have been a few hiccups, particularly with NFS Ganesha performance, although I have been informed that this is possibly due to the outdated version that we're running, because that's what's bundled in the official Ceph OCI images. All right, so how big is our current fleet? Well, this is my fleet. This is the current inventory of our Summit base and Tucson test stand. We've excluded the USDF because it's Ceph, but not Rook Ceph. We've enabled OSD encryption on all of our clusters, and we haven't had any performance issues with it, kind of surprisingly. Of our currently deployed clusters, the only ones using spinning Rust are used for dev tests, as these are older servers at the end of their life cycle. I was starting to get excited about being finally being free of spinning Rust. But the largest cluster that's currently racked and stacked is back to spinning Rust again, because the $1 to terabyte ratio of NVMe has been going in the wrong direction. And so I'm hoping by the end of the year to have our largest cluster up, which will be over 1,100 OSDs. So one of the enormous benefits of Rook is it allows for a gitops model for storage provisioning. I'm sure nobody in this room has ever been looking at shell history in the middle of the night trying to figure out what commands the last guy ran, even if the last guy was you, before the dumpster fire ignited. Rook isn't a gitops tool by itself. It configures Ceph based on Kubernetes resources, but it can be combined with any number of Kubernetes CI/CD solutions, and you've probably heard of them, Flux, Argo CD, Fleet, et cetera, to move your configurations from cut and pasted shell commands into a Git repository. Changes can be reviewed by other team members in a pull request or merge request before being made live. CI tools can be used. It is amazing how many problems are caught by even a generic YAML linter. Provides a configuration history of who did what and when, and can be rolled back when things go wrong. This is what our current GitOps workflow looks like. Probably needs some simplification. All of our Rook resources are in a public Git repository. Changes are made by pull request into the dev branch. That branch always has at least one dev cluster on it to pick up changes. Mergify is used to automatically open PRs from the dev branch into the master branch after they're merged. We have a production branch for each of our internal sites, which is basically used as a tag. It gets manually updated to a point in time in the master branch. This allows the entire site to be quickly rolled back if there's a problem. We also use Renovate to automatically open PRs to bump the version of the Helm charts we use. This includes the Rook Helm charts. Travis made a release of Rook yesterday, and PRs were automatically open to bump Rook in our environment for us. And that's it. Are there any questions?
So before you started all this, you already had Kubernetes on bare metal, I assume?
It was concurrent. So this was part of us bringing Kubernetes onto bare metal.
Do you have any Kubernetes thoughts that you orchestrate similar to this?
I'm not sure I understand the question.
Well, I guess, are you using like a Kubernetes distribution? Or are you just
Oh,
using,
yeah. So we use RKE, which is Ranchers, so it's RKE2. We just finished migrating from RKE1 to RKE2. I do recommend it. It's been really solid for us. RKE2 actually changed this model a little bit, and it makes it much more compatible with configuration management. So our provisioning process is that we pixie boot. We use the foreman to provision our nodes. They're currently all EL9, all Linux 9. And then Puppet installs RKE2 and brings it up. There's a manual step that's needed on a new cluster to set up a token to allow RKE2 to assemble the cluster, but then it's up and running from there on its own. And then we use Fleet as our CD solution. And so once the clusters bring up, there's a manual step to add that cluster into Rancher. And then from there, it automatically starts deploying everything onto the cluster. So the rebuild process for a cluster is fairly low touch. It's not quite zero touch, but it's pretty low touch to rebuild. And we do regularly rebuild our development clusters. Any other questions?
I'm just curious about your environment at the observatory. And was there anything special or different that you guys are doing up there because it is so far away and you can't reach it, and or like, so when the telescope takes down data, are you writing to RBD's file system, and are you mirroring that in the other clusters in the US?
Okay, so the flow is data comes into the DAC, and the DAC actually has at least, it's sized to have at least 72 hours of data in it. So that's the first place the data is. Within seconds from that, it's transferred from the DAC onto the LSSD CAM diagnostic cluster nodes. And from there, it's transferred into FITS formats, and then it is pushed out to 2 different S3 instances. One is local to the summit, and the other is at the USDF in California.
Okay, so S3.
Yeah, and our time budget for that process is 7 seconds. So data is very quickly ends up in 2 different RGW instances on different continents, right? And then we have processing that goes on from both ends. The rapid analysis processing for alerts that get sent out to clients happens at the USDF in California, but we also have processing that goes on at the summit, like scientists involved in commissioning processing data, and we run rapid analysis there as well.
Cool, thank you.
Yeah.
I was curious about the life cycle and upgrade of a Kubernetes cluster. Is like something that is like hands-off as well?
Yes and no. So it depends on the nature of the update. So as I just mentioned, we went through a migration from RKE1 to RKE2, and that is not an in-place migration. That is a reformat and start from scratch type upgrade. But the regular updates is pretty low friction. So we do updates once a month. So for example, we were going to go from like Kubernetes 1.31 to 1.32. So 1.32 gets deployed into our dev environment, and it sits there for a month to see if there's any problems on any of our test clusters. And then we do a rolling update of different sites once a week. So our Tucson test stand will get updated 1 week. The next week, our base facility will get updated, and then the summit finally that. So there's actually hopefully a lot of sort of scream testing that's happened before things are on our most important production site. And it's pretty low friction. It's basically updating the RKE2 RPMs, and that's driven by Puppet. So we stage the changes in a different Git repository, our Puppet control repository. We merge those, we force Puppet runs, and then we actually do a reboot during the daytime. Astronomy is kind of unlike a lot of industries in that our important time is at night, so we do a lot of maintenance basically in broad daylight in the middle of the day.
Thanks.
Hi, I thought I heard that you said you had certain nodes, workers that had local NVMe that were kind of like special snowflakes, right?
Yep.
I was wondering what kind of workloads that you needed that for, and yeah, basically how you kind of are handling that, or if you're looking to migrate away from it, or.
I would love to migrate away from it. We just needed the latency, basically. So there's 2 real drivers of that. One is InfluxDB, the other is Kafka. We also are using Postgres through the cloud-native Postgres operator, and it's getting close to needing that as well. We're starting to have situations where replicas breaking, and I suspect it's because we're just getting latency piling up and the replicas can't keep up with the primary. And so really it's just coming down to we need lower latency. So we're using a local storage driver for that. I would love to have that on Ceph and get rid of those special snowflakes, but we just had to do this for the performance.
Yeah, I was also wondering if you had looked into basically presenting it as a replicated set, but then having it essentially that OSDB close to where the pods are living as well.
Well, I mean, to get the properties of Ceph with like replication, you're going to have multiple OSDs, and assuming your failure domain is like host, that means you're going to be speaking to OSDs on multiple hosts anyways. So your latency is still going to be bounded by the furthest away OSD in terms of time, and so having some locality only save you some bandwidth on your switch interconnect.
Sure.
Yeah.
Thanks.
Anyone else?
Yeah, so you and I think, have pretty similar setups in the same way, local NVMEs for scratch space and stuff. On Monday night, you mentioned the memory requirements for, rebuilding an OSD.
Mm-hmm.
I was just curious what your, kind of OSD resource, specs look like on your NVMe clusters.
It varies because we've got a whole bunch of different clusters that, they're not all completely homogeneous. But typically on a performance system, we allow for 12 gigabytes. And we found that we need that for OSD recovery. OSDs don't normally use that, but we've seen sometimes when OSD is recovering, it really spikes up to that.
Yeah. Have you ever gone higher and just saw that there was no benefit and went back down to 12?
The OSD just doesn't use it. Yeah, so the 12 gigabyte is a limit configured on the Kubernetes pod.
Okay, gotcha. And then I was also curious, is it all triple replication, or are you using erasure code?
We use a mixture of both.
Oh.
So typically for in-cluster RBD, so Kubernetes PVCs, we use 3x replication. For the various different RGW instances we're using typically some form of EC. The largest one at the summit is actually 8+3 currently.
Got it. Okay, great, thanks.
I was wondering some about your Kubernetes architecture and how you're exposing the clusters to the consumers.
Okay. So typically, not typically, in all cases currently, we're not exposing Ceph external to the Kubernetes cluster. So Ceph is on Kubernetes internal overlay network only. So if you want access to that external to the cluster, we're exposing it either via S3, so we use Kubernetes ingress controller to expose that, or we use Metal LB to expose a service in the case of NFS for NFS Ganesha.
All right. And so you don't have any use cases with external clusters or cross namespace or anything like that?
I wouldn't say that we don't have potential use cases, but we're not currently doing that.
Okay.
If we wanted to, for example, switch from NFS to CephFS on our clusters that are running Jupyter notebooks and they need to talk to the remote storage, then we would have to expose Ceph in some way or use a solution like Submariner to plumb the Kubernetes overlay networks together between the different clusters.
Right. Thank you.
Anything else? Great. Thank you, guys.